basically what I'm going to talk about. I'm going to first justify, excuse me, justify why Ray exists. Then talk in detail about reinforcement learning with Ray. I'll do a little intro to what reinforcement learning is for those of you that may not be that familiar with it. Then I'll do a demo with RLlib in a notebook environment. And then I'll finish with some notes about how to adopt Ray, about the Ray community if you want to get involved, and so forth. All right, so first, why Ray? Why is it interesting? Why did it emerge? Well, it's really in reaction to two major trends we've observed over the last several years. The first one is that if you look at the sizes of neural network models that people are developing, they are going up by a factor of like 35 times in size every 18 months. You know, in contrast, this is a log plot. So in contrast, Moore's law goes up, 2x. Ergo, you have to do distributed computing if you're going to keep up. If you're going to actually, finish things in a reasonable time, you're just going to have to go distributed to accomplish this. And at the same time, over the last decade or so, we've seen, a tremendous increase in use of Python for, mostly driven by these sort of data science workloads. And so we have this real need to then make it easy for people to scale Python to clusters in a relatively easy to use, but also robust fashion. So that's really the motivation for Ray. It tries to solve this problem. Here's a list of typical tasks or choices you make when you're building machine learning or AI algorithms and systems. Everything from ETL on the left and turning your data into features to stream processing because you might have latency requirements to score data fairly quickly or update models. You're training on the fly. Hyperparameter tuning to find the right model structure. Training to actually, once you've found that structure, to actually do the training on data. Simulation is important for systems like reinforcement learning, like game engines and so forth. And then the last one, which is kind of blocked by my dialogue here, model serving. Once the models are developed, you need to serve them, in particular, say, for doing streaming, scoring on streams. So, oops, I hit that twice. Sorry, let me go back quickly for a second. There we go. So all of these things require distributed implementations if we're going to scale them to perform in a timely fashion to meet the compute requirements that we have. So the vision of Ray is that let's build a framework that's flexible enough to support all of these different kinds of compute patterns, memory access patterns, and so forth. Everything from typical data flow scenarios to very arbitrary kind of systems like simulators, and make that available primarily to Python initially, but it's actually flexible enough that we can support other languages. And there's an early version of a Java API even for this, for those of you that might happen to be deploying stuff on the JVM. And then build domain-specific libraries that address some of these different needs. Here's 4 of them that we have right now. Tune is for hyperparameter tuning. Ray SGD is specifically to accelerate distributed stochastic gradient descent, basically training for PyTorch and eventually TensorFlow. RLlib is the one we'll talk about today for reinforcement learning, and there's also a new module called Ray Serve. The adoption's been pretty good. We've seen a lot of growth over the last few years. Maybe what's most interesting, when I look at a new system, I want to know who's using this, how robust is it? And you can read about how different organizations are using it at ray.io, which is the main website for Ray. That's where you can find access to the documentation, the Git repo, and so forth. The biggest user is actually Ant Financial here in the middle. They're sort of the analog of Stripe in China, the spinoff of Alibaba. And they run Ray on clusters of thousands of nodes for all kinds of stuff, actually, not just machine learning. Okay, so that's sort of the gist of the problem that Ray is trying to address. We'll cover that a little bit more detail as we learn more about RLlib and sort of the particular challenges that Ray was designed to solve. But let's dive into RLlib for machine learning. Reinforcement learning. There's actually a link, rllib.io takes you straight to the documentation in Ray for RLlib. So it's a sort of a convenient shortcut. All right, so again, we're going to talk about RLlib here of these libraries. well, we have other stuff online that talk about these other libraries if you're interested, and I can certainly follow up with anybody if you want to talk about those as well. Okay, so if you don't know anything about reinforcement learning, the gist of it is this, that I have some agent who's interacting with an environment. The agent is observing the state of the environment, making a decision about what action to take next, and then observing the reward that is accrued by taking that step. If there is a reward, some things, the only reward is whether you win or lose the game, that sort of thing. And the goal of this agent is to maximize the cumulative rewards after going through a session, if you will, with this environment. So some specific examples fall into these categories, and I'll walk through them one at a time. The first one that you've probably heard about already is gameplay. So initially there was a lot of success training systems to play like arcade games or online games like I forget what this one is in the middle. But the most famous example was actually beating the world's best Go player, the AlphaGo system, Google's DeepMind division. That one was amazing because the state of the game of Go is so enormous, so much bigger than chess, that a lot of people thought it would be maybe a few more decades before ML was mature and sophisticated enough to actually achieve this level. And yet the DeepMind team, using reinforcement learning, was able to accomplish this much sooner. It was actually these sort of game environments and the success of reinforcement learning in these environments that turned reinforcement learning from being kind of an obscure part of the ML space into something that became extremely hot almost overnight. It's also been used in various robotics tasks, like training a robot to do different tasks, training mobility in robots, and also autonomous vehicles. Now, these are kind of all maybe more research and interesting for the curiosity factor, but maybe not yet that practical for most of us in typical businesses and industries. But that's starting to change too now. So we're starting to see optimization of business processes like assembly lines. And I picked a state-of-the-art picture of an assembly line from probably the 1920s. But also things like regular business processes. How can we not only model them, but optimize how they work? You could think of also like routing. We have the traveling salesman problem that's NP complete, but maybe we can get really good, heuristically good solutions using RL. System optimization, like optimizing how data centers are heated and cooled, optimizing network topologies, hopefully better than this wad of cables we see on the left here. There's some really interesting applications in advertising, like ad serving and recommendations. This diagram is taken from a paper that describes how YouTube is now using reinforcement learning to optimize the videos that it recommends to you. Another really interesting case along this line is Netflix is using RL to optimize the images it shows you of videos or movies so that you are more likely to pick something or find something interesting. And then finally, people have always applied the latest technologies to finance to try to get the upper hand on trading. It's also being used, though maybe more practically, for risk analysis problems. Okay, so these are a bunch of applications that people are using. Maybe some of these fit into whatever domain you're in. Just to peel the onion a little bit, let's talk about AlphaGo again and map what it is doing to that sort of high-level diagram I gave you at the beginning. In this case, the observations are the state of the board. Here's a few snapshots. The actions are, where do I place stones? And the rewards are pretty simple. It's either I win or lose. You could say that some intermediate steps are better than others because of the state that they put the board in and your relative advantage. But usually it's not scored that way. It's just win or loss is how it's scored. And that's what we're trying to optimize. And then there's this neural network that they use. Conceptually, it's shown here, where convolutions are used to kind of map particular arrangements of stones that represent strategically advantageous configurations. Okay, so how does this tie back to RLlib then? Well, so we have this wide range of possible applications and more coming online all the time. some of the initial choices you make are like the architecture of your agents. Do I have just a single agent, like we've sort of talked about so far, or maybe multiple collaborating agents? Maybe they're organized hierarchically. And there's also this whole emerging technology around offline batch, which is, how could I build a system based on like historical data? I can't run my chemical plant with a RL system to train it. That would be a little dangerous and too expensive. But maybe I can take the logs of my chemical plant, of everything that's happened in the past, and use that to build an optimal model. RLlib then tries to address all of these things with a fairly intuitive, mostly declarative API that generalizes over all the algorithms that exist that you might want to use. We'll actually look at PPO as an example. Proximal policy optimization is called. And all of that runs on top of Ray, which handles all the distribution around a cluster for all of the different stuff that has to happen. This is an eye chart of some of the algorithms that are implemented in RLlib. These are all links to the particular library spots. You can actually, the easiest thing to do probably is just go to the ray.io or maybe the RLlib.io link and then search in there for these particular algorithms that you're interested in. But once again, I'll make the slides available as well. You can even use RLlib inside of Amazon SageMaker if you want. All right, let me actually do a demo here. So I'm going to switch to my browser. That's not the key I want. Here we go. All right. Now I'm going to use the Hello World of reinforcement learning, which is CartPol. Hello World, if you know that reference, it was sort of like the starter application for every sort of programming system. When I was doing Hadoop, the Hello World was like word count. In reinforcement learning, it's a CartPol. This is a screen grab. You'll actually see it live in a moment. But it's the idea that I have a cart moving back and forth in one dimension, and I want to balance this vertical pole. So as you can see, this configuration right here, it's obviously, it looks like it's going to fall to the right. Then that means I probably need to move the cart to the right so that I don't let it fall, and so forth. So the idea is that you train a system to do this. And it's a really good basic system, easy to understand, but it lets us mostly focus on what we care about today, which is how to use RLlib. So to start this, and this actually is taken from the tutorial material that I'm developing, so it should work, but you never know until you actually run something. So restarting my kernel, so it's good. There's a couple of links to papers that describe the algorithms and the history of this idea, but we're actually going to use a newer algorithm called PPO. So the first thing I do is I import Ray, and then I also import the PPO algorithm from within RLlib. I need these imports for some of the utilities I'm going to use. Now, it turns out model checkpoints are going to be written to a directory that I've defined here as a checkpoint directory. There's also going to be some stuff that's written into my home directory in a directory called Ray_results. I want to clean those out because they can confuse some of the things that we're going to do later. So it's best just to start with a clean slate. All right, now we are going to initialize Ray. And if we were running in a cluster, we would pass an argument that says, here's where my cluster is, go attach to it. Now I want you to run everything in a cluster. I'm just running on a laptop here. The argument I passed is just so I could reevaluate the cell and not have Ray complain to me that it's already initialized. There's this nice dashboard that's useful for seeing how things are performing. Is it nicely load balanced and actually even profiling particular applications. So I'm just going to show it to you. We won't actually use it, but these are all separate processes that are now running on my machine. I basically have 8 hardware threads on this laptop, and it spins up 19 workers. These rollout workers were already started by Ray for RLlib. So if I go back here, and we just looked at that cell. Right now we're going to actually start up and use CartPol. There's some configuration settings we could do. I'm going to do 10 iterations of training. I could set up a lot of configuration like the size of the neural network and so forth. I'm just going to go with defaults right now. I'm going to initialize the PPO trainer inside of Ray. Use the environment I just defined. So it actually has this built-in integration with the OpenAI Gym environment so that we don't have to worry about importing all that stuff as well. This is a pretty popular environment for testing machine learning algorithms, learning, and so forth. So what's going to happen next is I'm going to iterate over basically 10 times, and I'm going to train this agent, and it'll actually get smarter every time. It's going to remember what it's learned. And then I'm going to capture the results that came back, and we'll look at some of the data about, you know, how good is the reward and so forth. The maximum reward is 200. It turns out the default neural network is way kind of too sophisticated, and it's actually going to learn really fast. So you know, often you would dumb it down a little bit so that it takes its time learning, but we'll see what happens here. So now we're going to, you know, run for 10 loops. Each loop is going to train and try to, you know, improve its ability to perform. And it should be printing out something really soon now. There it goes. Okay, a little panic attack there, wondering if it's not going to work. You can see that the max reward is getting better, and it's already getting very close to 200. And in fact, it's going to just, you know, for the rest of these 10 iterations, basically be at 200. So once that's done, then I'll actually just load some of the interesting data here in a data frame so that I can plot it. Also, you know, I'll be graphing it as well as just plotting it here in a table. It'll take another moment or so for this to finish. 2 more cycles. Okay, we're done. And then you can see that it plots both the mean reward. So, you know, it was still like jittering and trying different combinations. Some things didn't go so well. And so, you know, initially it was kind of poor, but towards the end, it just got really good at even on the mean, on the average, it was learning very well. And it very quickly developed the ability to achieve the maximum reward. This episode length is the number of steps it took. It turns out that the incremental reward is 1 per step. So this number is pretty much in lockstep with the reward mean, but that would not normally be the case in another system besides a card. I've got a wire in my way, sorry for this. Okay, and let's just plot this. I'm going to use Bokeh to plot this data just for fun, and we can see basically what we just plotted, that it quickly, the max reward quickly converges to 200, but the mean slowly got better and better, so that it actually got really good at playing this game by the end. And we can also print out the information that was generated from the model, you know, the structure of the model, what it learned, and so forth. So this is just a pretty print utility. It's part of RLlib. I just used it to dump this information. We could and actually see this this thing actually running. It'll take a moment. There it goes. So it's actually replaying the second checkpoint. So it's going to play replay a bunch of the games, some of which were not very successful, others of which had better durability. Actually, the first one was quite good. It scored 200. This one looks really good too. You can see most of them are actually quite good. Occasionally we get a real dud, but most of them are playing it very well. And we're almost done. Let's see. Forget how many episodes it has. There we go. So we're finished. And then at the end here, you can actually, so some of this information was written to this directory in my home directory called Ray Results, and we have an integration with TensorBoard, and that's something you could use to explore the parameter space. I'll just open that up, and you can see kind of details about what it learned and you know, how it did and so forth. So if you're used to using TensorBoard, you have this nice integration for exploring this information. All right, that's basically it. We won't go through the exercise. This is obviously a demo, not an exercise or tutorial. Let me go back now to the slides. Okay, so just a little bit more about what RLlib has to achieve in order to be this flexible tool. If you read through the papers of different architectures and algorithms that people have developed, you see that they have different structures. You can see 2 different ones right here, especially on the left-hand side. And they also did different steps or different computations as part of the process of reinforcement learning in different places in this architecture. You know, calculating things like the policy, the loss, and so forth was done in different places. Excuse me. So what that meant is that we really needed to define really good abstractions for the different aspects of reinforcement learning, make them composable so that you can relatively easily change these configurations for the kind of architectures that you're building, whether you're using an existing algorithm or prototyping new ones. We wanted code reuse across all of the deep learning frameworks, whether it's TensorFlow, PyTorch, et cetera. And of course, scalable execution is really essential. Doing something like training a system to beat the world's best Go player, you're obviously going to need to do massive computation because you're going to be running lots and lots of sessions of that game, and you'd like to do that in parallel and learn the best you can. And then make it as easy as possible for people who don't want to learn about programming or are more interested in algorithm development, to be able to use the system. Now, there was a question here. Let me go ahead and answer that. So how does ARM continue to increase episode length after iteration 2 and the max reward is obtained? Where does the gradient come from? Oh, it looks like the max reward is not the source of the corrective gradient, it's average reward. Thanks. Yeah, okay. So they answer their own question. Yeah, so we're basically, each of those training runs is actually playing the game multiple times, but because it was learning, it just got really better at picking good choices and not exploring essentially bad choices later on. There's a whole lot of other things you can configure, both the structure of the neural network, the batching that it uses, the number of iterations that you run, and so forth. So that's the sort of thing you would play with when you're trying to, optimize for performance, but at the same time optimize your use of compute. A question also: how do you handle scalability? What it actually does this behind the scenes. So maybe I should have switched to the Ray dashboard that I showed you briefly while it was running. But if this were in a cluster, it would be scheduling work around the cluster. All the different things it has to run. It basically moves that compute over to each node and then runs it there. So it handles all of that transparently. There's obviously some configuration you can do if you wanted to reach down underneath. Well, there's actually some you can do at the RLlib level, and there's some configuration you can do, like when we initialize Ray itself. There's things we can define, like how many GPUs there are, CPUs, and so forth. So, and we're actually building a lot more around user configurable topology as well. Okay, so anyway, all of these general purpose requirements and flexibility were really kind of a big inspiration for Ray. The researchers at Berkeley were building these systems, mostly reinforcement learning systems, and realized that the tools they had available were becoming more burdensome than helpful. So they decided to step back, work from ground zero in a way, build something extremely flexible underneath, which is Ray, and then layer on top of that these libraries for these particular compute problems they were facing. And some of those variant kinds of compute challenges are, simulation, the game engine, sort of very diverse kind of compute, CPU access, memory access patterns, much different than, say, streaming data or just, loading a big data set and manipulating it as a SQL query or something. You also need an efficient server for serving policy when you're training, when you're actually running. And then these different architectures for how agents are used. Someone asked online here, what I think to be honest, it's not an easy name to Google. Most of the things like the Twitter handle is Ray Distributed, the GitHub project is Ray Project. So, one of those words, it's not unique, but they thought it was just a good word to kind of capture the essence of being lightweight and direct and to the point. Okay, so with all of these diverse compute patterns, this is what Ray was designed to solve in a relatively easy way. And we think other proof points have been our hyperparameter tuning library and so forth. But you got to have good performance. It's great to have flexibility. Abstraction is a beautiful thing, but if you don't satisfy performance requirements, then it's not so great. But so far, it's proven to be very performant compared to some custom, hand-rolled implementations of some of these algorithms. All right, so just briefly to wrap up, and then I'll take some more questions. How would you get involved in using Ray and RLlib? Well, first of all, just as a side note, if you're using, if you're writing other Python code that uses some of these multi-processing APIs, excuse me, like async IO, joblib, and multiprocessing.pool, which are all kind of limited to one machine, you know, they're multi-threading and so forth. The nice thing about using the drop-in replacements that Ray provides is that they just sort of break the node boundary. You can now just, with these relatively simple changes, now scale your app to a cluster. So here's some more information. Once again, ray.io and RLlib.io will take you right to information that you might care about most. The tutorial stuff, we're rolling out that starting later this month as well, but the RLlib stuff will be released next month, and you can find out more information at our events page that I mentioned earlier. If you need help, actually the best place to ask for help is on the Slack channel, Ray-Distributed. There is a Google group, Ray-Dev, but it's not as active as the Slack channel, so that's what we recommend. And you can certainly reach out to me too if you have specific questions and you don't feel like they're getting answered or something. Anyway, thanks so much for listening. I'll be happy to take your questions. Once again, you can contact me on the left. Do check out our Ray Summit Connect series that starts this Wednesday. We're really proud of the initial session in particular with Michael Jordan and Jan Stoika. But anyway, let me go ahead and answer questions. You can put them in the QA. I'll exit out of this so I can see the chat window as well, and stop sharing my screen for a moment, and then I can take questions in either venue. Okay, so let's see, what have I not answered yet? How can I apply your technology to my project? I'll tell you what, I'll look at this offline. It'd be difficult for me to tell right off the bat, just looking at a new project, but I'd be happy to chat offline. Please let me know if RLlib is the ML pipeline. That's a really good question, because it really is designed to be a tool that you can use in a larger framework. We have aspirations to build pipelines like everybody else does, of course, but the reality is that we mostly want to solve particular problems in the way that Ray does best, and RLlib is a good example. So it is, I showed you code, actually, how to use it with Python. So it's actually really easy to integrate it with pipelines that you might be using, like MLflow or whatever. So it's designed to be flexible like that. And also, someone asked about the pricing. This is all open source. It's free to use. Anyscale is developing some commercial services around Ray, but Ray and RLlib are and will remain open source and free to use. Another question, what type of project do you suggest for someone to do that wants to learn RL and Ray? Well, I'm hoping that the tutorial material that I'm writing will be a good place to go for that. I know that AI Camp is also a really great resource for learning about these topics. You could also check out OpenAI and FastAI. They provide a lot of good materials. I do like two things. One, starting with relatively simple examples that are already well baked, like cart-pull is the famous one I mentioned. An alternative, though, is to think about a simple problem you have and then see if you can adapt some of this technology to that. In particular, if you have a problem that you already have a reasonably good solution as a baseline, and you can see if you're actually getting better by using something like RLlib, is very helpful as well. Okay, any other questions? Let's see. I think maybe we've covered all of them, and certainly all of them in the Q&A. What about in the chat? Is there any that we haven't looked at yet?
I think most of them is already in Q&A. From the top one, I think there are one. Let's see. Oh, there's a question. I'm not sure this one answered. How do they handle the scalability? Is that one already discussed in the Q&A?
I did talk about that a little bit, that behind the scenes, RLlib is using Ray to do scaling of the various tasks that have to be done for training for the neural network stuff and so forth. It's a bit opaque at the moment, and maybe I should have showed the dashboard that shows a little bit about what's going on, but it's handling that for you, whether it's locally on one machine or on a cluster. And by the way, there is built-in awareness of GPUs and things like that when you need them also.
Great. Is any, if you have questions, please type in the Q&A, and you can also type in the chat if you want. So we will go through that. I see another one coming up.
Yeah, there was a couple. One was using how much work has been done with RL and NLP. I'm not really an expert on NLP, so I'm not really sure. I think there is some work that's being done, especially when you have sparse data sets. Years ago, I did a small project with with an insurance company on analyzing their call records, meaning, customer calls in to complain about their claim form or whatever. And so they tend to be very terse conversations full of jargon, excuse me, and something where you may not really be able to use a lot of the traditional approaches as easily. And so there has been some work, but I'm just not that knowledgeable about it. Someone also asked about the GitHub link. Let me just open that up in my browser window to remind myself what it is so I don't forget. And then I'll paste it in the chat window. Okay, yeah. So I'll put that in the chat here. Actually, let me make sure that I'm chatting to everybody, not just the panelists. Okay, so there's the link to the Git repo. Once again, though, you can actually get to it if you go to ray.io. There's a link for the GitHub. Also, our blog is, there's a lot of intro blogs that might be useful for getting started with Ray and some of the other tools. Not as much about RLlib yet. We need to fix that. Let's see what else. Someone is asking how big the data set could be. That's kind of an interesting question because on the one hand, it's only limited by memory in the usual way and your file system. Ray is not, if you compare Ray to systems like Spark, where they have a very specific model for laying out data efficiently, structured data in memory, Ray actually leverages some of the corresponding technology that emerged out of that, like pandas, and also, what's the name of it? I'm blanking on there's an in-memory thing that I'm just completely blanking on right now. But anyway, but really the main point though is that Ray is designed to be general purpose. So it's actually really designed to handle like distributed object graphs. If you think like about a traditional object-oriented program and how you have this sort of graph of data that's linked around, that's what Ray's really good at handling. It can also handle these kind of structured data, but it's not really its core strength. So they're really, what you find is if you're working with big data sets, you're going to have to structure your apps so that they try to avoid loading everything in memory if possible. But also when you start Ray, some of the configuration information you would pass to it would be to set things like the size of this in-memory data store that it uses to cache data and so forth. So there's a little bit of tweaking you would have to do when you're running at really large scale. Okay, let's see. I'm going through more questions here. Can you explain the architecture, async, DQN, et cetera, in one of your slides? Yeah, that one is, that's a relatively new, so DQN was one of the earliest, distributed queue network is one of the earliest integrations of neural networks with so-called queue learning, which is one of the original algorithms for reinforcement learning. And async DQN is designed to make that work efficiently when you're in a clustered environment where you can't necessarily tolerate the performance hit of doing synchronous communications, like calling for something and waiting for an answer. I don't know a whole lot beyond that myself about this algorithm. I haven't looked at it in detail, but that's the idea. It's designed to be if you're going to use DQN, then you would want to use async DQN if you're running in a cluster. However, I should say that what people have told me who are more experienced in RLlib or reinforcement learning in general is that it seems that PPO has become really popular for this stuff, and it naturally naturally fits a distributed compute model as well. So someone was asking, is Ray a platform? Is it available online? Is there some sort of console? Really good question. So basically what the sort of product ideas we're pursuing at Anyscale are really towards making it easy to just run Ray in a hosted environment without having to do a lot of stuff yourself. setting up a cluster, whether you do it yourself in Amazon or on devices in your own network, is fairly straightforward. It's not too involved, but it's work that a lot of people don't want to do. If you're pure data science and don't know a whole lot about system architectures and don't want to worry about that, then this is what we're going to try to make easy for you to do, is more of a commercial offering. So it's not yet available online, but we're working to make that so for you. Someone is asking if I know of anyone using Ray or RLlib and epigenomics. I don't know of anyone myself. We do hear all the time about new organizations that are trying it out, but I can't recall any users in that space. Is there a Docker container with Ray that you would recommend? This is something I think we actually need to do. We haven't done officially. However, there is, in other words, we haven't actually built Docker images in Docker Hub that you could use, but there is actually commands available in the repo for building your own Docker images. And that's probably what you should start with for now until we do an official one that would be easy to use. Part of the problem is there's a lot of stuff that you would pull in when you're doing reinforcement learning, like TensorFlow and PyTorch, that you don't necessarily want if you're doing just RL or just basic Ray. So, excuse me. So a challenge would be, we'd probably really want to do several Docker containers or Docker images so that you can pick the one that has all the stuff you want, but not the extra stuff you don't need. So that's one of the things that's kind of held us back there. Back in the chat window, someone asked, what types of business or science problems is RL good with? I tried to give you a sense of that in the slides towards the beginning because it is a really good question. This was one of those exciting things a few years ago because it was, beating the world's best Go player. It was amazing at playing Atari games. And it was being used for things like robotics. But, how does that apply to me? When I'm doing business process modeling or recommendation engines for my website. And that's the kind of stuff that's starting to emerge now. So what again, I'll make the slides available. What I suggest you do is Google some of those topics like, recommendations and reinforcement learning, and you'll find some of the papers and some of the blog posts that have been written about this kind of stuff. Someone is asking if they can have the demo code. As a matter of fact, you can actually, this particular example, I'm going to check into GitHub for our Academy repo. It's kind of rough around the edges, but you can actually start playing with it now if you like. And I'll type that link in here as well. So if you go to HTTPS, and this, let me just get rid of that. So github.com, Anyscale Academy is the work in progress where I'm developing the tutorial material. It'll be completely open source also. You'll see an RLlib folder there. You can start playing with those if you want. Feel free to report issues that you run into. I'm trying to clean up a lot of stuff. It's really rough around the edges, so be patient with me. It'll be a much cleaner in a few weeks, especially the core Ray stuff, and then the RLlib stuff we're releasing probably in early June. Okay, any tutorials for integration with SageMaker? Really good question. I don't have that on my list right now. We don't have any that I'm aware of. I'll see if anyone has written one, and if so, I'll tweet it on the Anyscale Twitter account. That's Anyscale Compute. I'll put that in here. I think I got that right. And also the Ray Twitter account, which is Ray Distributed. But I don't believe there's one yet, and I'll probably write one myself at some point, but I haven't done so yet. I would also check the SageMaker documentation. They may have their own information about this already. Okay, did I miss anything? Let's see. Someone is asking about NumPy and SciPy. What's interesting about those is we do a lot of applications ourselves, and people use Ray with those libraries all the time. So Ray is pretty agnostic about the kinds of libraries you're using on top of it. RLlib leverages things like PyTorch, TensorFlow, scikit-learn, and so forth. So I actually often use NumPy in particular when I want to represent data in an array where that makes the most sense. So in fact, when you go through the Ray tutorial material at that Academy site, you'll see use of NumPy quite a lot, as I'm using it for demonstrating various sample applications. So that, I think, is what I think they did well with Ray. And I say they because I joined the organization after Ray was released and after the core ideas were designed. So they did a really nice job of taking boiling the abstractions down to their essence, so that if you really do need to do low-level distributed computing at that level, as opposed to something higher level like RL, you can really do it with not a lot of code and with a reasonably intuitive sense of how to write that code and let Ray do most of the heavy lifting for you. If I compare that to other toolkits I've worked with for distributed computing, most of the time they're written from a developer perspective of, all right, here it is. Here's everything you need to possibly build the world, but you really have to take the energy or the time to master it. I think Ray does a good job of flipping that and thinking about people who need this but don't want to spend a lot of time on this. How would they go about it? And so